Hello everyone, I am Mohammad Siam, a master's student at University of Dhaka. I am presenting my paper, An Exploratory Study on the Impact of Change-proneness as a metric in Black-box Test Suite Minimization. Software testing is a process to validate whether a software performs the way it is intended to do or not. In modern development, before publishing a new version of software, the entire test suite is executed. This is known as regression testing. As software evolves, the size of the test suite grows. This can cause excessive time and resource wastage. Thus, test suites need to be minimized. But removing necessary test cases can reduce the bug detection capability of the test suite. Minimizing test suite while maintaining its bug detection capability is known as test suite minimization (TSM). Test suite minimization approaches can be divided into two ways. White box, which analyzes production code, quite accurate but not time and resource efficient. Black box, on the other hand, relies on the test code only. It's quite practical and efficient. Black box test suite minimization approaches are getting attention due to its practical use case. Existing black box approaches utilize test log, textual diversity, structural diversity, and semantic diversity as metric. But none of them are effective, efficient, and lightweight at the same time. Can any other metric address this gap? Change proneness comes here. Change proneness is the likelihood of a class undergoing a change. Literature says change prone classes require more maintenance effort, contains more bugs, and has been used as a predictor of bugs. Thus, our hypothesis is test cases that target the most change-prone classes have higher possibility of detecting faults. So we want to know if change-proneness can be considered as a metric for test suite minimization. This is the overview of our approach. We first extract change metrics to calculate the change-proneness, generate call graph, and find a test case class dependencies, and finally rank the test cases according to the change-proneness values. So first, let's start with extracting change metrics. While extracting change metrics, we extract change count, number of commits performed since the file is created, lines added, deleted, and modified for each changed files. But due to file restructure, there may be duplicate entries. For example, in the given table, the class CSV parser was moved from one directory to another. So we need to aggregate these duplicate entries. To aggregate, we add up the change metrics, such as changes, insertions, and deletions. Since the total number of changes is the change encountered by both the old and the new versions. So here it's added. And for the total commit count, we take the maximum among the entries as it encompasses all the commits across versions. We extract those change metrics from two commit ranges, inception to current version and from the last stable version to current version. Then we calculate the change proneness in two measures, change frequency and change extent as shown in the equations. In order to understand the dependency of the test cases, we generate call graphs of the test code using Java call graph tool. In order to map the test case class dependencies, we identify the class invocations from each test case. For a given case, we identify the direct call invocations, subsequent hierarchical calls, and the test class itself, as the newly added or modified test cases may be helpful in detecting faults. We then score each test case based on the change proneness of the depending classes. A test case can depend on multiple test classes, each with its own change proneness values. We use 8 statistical measures such as median, geometric mean, etc. to aggregate these values. So after aggregating, we have the score of each test case. Finally, test cases with the maximum values are selected. We conducted our experiments on 15 Java projects containing 617 buggy versions of Defects4j in a Intel Core i5 9th gen computer. To evaluate the performance of our approach, we considered accuracy and execution time as the evaluation metrics. We conducted our experiments on 32 different configurations comprising of 2 change proneness measures, 2 commit ranges, and 8 statistical measures. And using change extent and change proneness from the inception, we found the best accuracy with geometric mean. Now, when comparing with the state-of-the-art metric diversity-based approach, change proneness achieved similar accuracy as diversity. It reduced the execution time by 114.5 folds. Thus, we can conclude that change proneness can serve as an effective metric for test suite minimization. So our contributions are, we formulated the quantification of change proneness, we proposed a novel black box approach, we provided a faster yet accurate change proneness metric, and we established change proneness as a test suite minimization metric. So that's all from me today. Thank you everyone for listening.